Hi guys, this is going to be a video about electron configuration. And so when we're trying to find the electron configuration of an atom, first thing we need to do is to find the number of electrons, right? If, for example, we had the atom sodium, Na, right? Well, we need to figure out how many electrons this species has. And so sodium currently has a 0 charge, and if we look at the periodic table, sodium is number 11 on the periodic table. So its atomic number is 11, which means that its number of protons is equal to 11. All right? The charge here, right? Charge is equal to the number of protons minus the number of electrons, right? So mathematically, if we take these two numbers, right, 11 and 0, and we subtract them, we actually get the number of electrons. And so if we do the math, 11 minus 0, well, we have 11 electrons, right? And so now we need to figure out where do we place those 11 electrons in sodium, right? So the way we do this is by using the periodic table. Okay, the periodic table gives us a lot of properties that are very useful to us, and it groups elements together by those properties, okay? And so for the electron configuration, it's useful to know where the S, P, D, and F blocks are on the periodic table, okay? The S, P, D, and F. So the first two groups of the periodic table, and remember the groups are the vertical columns, right? The first two groups make up the S block, okay? The last 6 groups, so groups 13 through group 18, make up the P block, right? There's a slight complication in that helium is actually part of the S block, right? And that has to do with the fact that the first energy level doesn't have any p orbitals, so it can only be s. All right? So we have the s block, the p block, everything in between the s and the p block. We have the d block here. And finally, down here, off to the side of the periodic table, below it, we have the f block. Okay? And so how does this help us, right? How do we find the electron configuration from here? Well, if we know the period number of the element, so the period numbers are the numbers that are over to the side here, and they start from 1 and they range all the way down to 7, well, those period numbers tell us the energy level of the highest electrons, okay? So these two letters here are going to help us with that, all right? So sodium, since it's in the s block, third period, well, that means its final orbital, is 3s, okay? Its final orbital, its final sublevel, is 3s, all right? So after we get the final orbital, well, we include all of the other sublevels, all of the other orbitals that came before it, okay? So if we label it, we have 1s, 2s, 2s for each of these blocks. This is in the p block, so 2p, 2p, 2p. So we have 6 2p's, and we have 1 3s. Okay, so the periodic table kind of tells us what the electron configuration is going to be. So our electron configuration is going to be, well, 1s plus 1s plus 2s plus 2s, right? Looking at the periodic table, 1s, 1s, 2s, 2s. Then we have 6 2p's. So 2p plus 2p plus 2p plus 2p plus 2p plus 2p. And finally, we have 1 3s. Okay? So normally we don't write the electron configuration like this. We take the electron configuration and make it condensed. So since there are two 1s's here, what we do is we write it in the superscript, just like that. So 1s2. 2s2, 2p6, 3s1. Okay? So, therefore, the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. Okay? 1s2, 2s2, 2p6, 3s1. This is where all of the electrons are in that atom. All right? So if we took another example, right? So let's say we had calcium, right? If we look in the periodic table, calcium is element number 20, right? So calcium, being element number 20, has is in the 4s position, right? That means its final orbital is 4s. So when we start writing the electron configuration, we know that calcium is going to end in 4s. Okay? So we have the 1s, we have 2s, 2p, 3s, 3p, right? That's all 3p, and then 4s, right? So if we write it down, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, that is the electron configuration of calcium. All right? The electron configuration of calcium. However, when we get to the electron configuration of the D block elements, so for example, if we had scandium, which has one more electron than calcium, right? Scandium is element number 21. Well, it's going to have the first 20 electrons, so those are still there. 2p6, 3s2, 3p6, 4s2. Now, there's a slight complication with the D block in that, so when we count it, we usually just leave the period number alone. Well, for the D block, we actually take one for the period number. Okay? So, we don't actually say 4D here. You would think it would be 4D because it's in the fourth period. However, it is actually 3D. Okay? So, the next electron is going to go into the 3D orbital. Okay? So, 3D1. Alright? If we go to the 22nd element, that would be titanium. So 22 titanium. Well, it has all of those electrons plus one more. And so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Instead of 1, it would be 3d2. If we had the 23rd element, which is vanadium, V, we have 1s2, 2s2, right? And so the electron configurations repeat quite frequently. Okay, they repeat quite frequently. And as we look at these, we might say, is there an easier way to do this? Well, there actually is an easier way to do this. Okay, there actually is an easier way to do this. So let's take vanadium, right? Vanadium was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Right? Well, how do we make this easier? Well, we can use the noble gas configuration. Okay? So if we look at vanadium, right? Look at vanadium at the periodic table. It is in the fourth period. Right? Vanadium is in the fourth period. So, to abbreviate vanadium, we're going to use the noble gas in the third period. We're going to go one period up, so from 4 up to 3, and we're going to go all the way to the right until we hit the noble gases. gases. Okay, the noble gases is group 18 at the very left or very right of the periodic table, right? So we're going to use argon to abbreviate this. Argon has 18 electrons, which means this accounts for the first 18 here. So we can abbreviate this by putting it in brackets, argon 4s2 3d3. Okay, so that would be the electron configuration for vanadium. All right. For example, if I had asked you what the electron configuration was for, let's say, big element, right? Let's take, I don't know, barium, right? 56 electrons. Well, I'm not going to write 56 electrons. I'm too lazy, right? So instead, what I'm going to do is I'm in period 6. I'm going to go one period up, so I'm in period 5. I'm going to go all the way to the right until I hit the noble gas that's above it. So xenon. That would be element number 54. Okay? So that means the electron configuration of barium, right, element number 56, well, the first 54 electrons are going to be covered by xenon. Okay? And now we need to fill in the final 2. And so this is in the s block, 6th period, so its final 2 electrons are 6s2. Okay? So this makes it a lot easier to see the electron configurations. All right? One final thing to note, right? If there's 3 ways we write the electron configuration. This right here, right? This was called the full configuration. This here is called the noble gas configuration. Well, there's also the box notation, right? And so box notation, we draw literally the orbitals on an energy diagram. So energy goes up this way, and we place the orbitals where they have their energies, right? So 1s has the lowest energy, then it's 2s, and slightly higher is 2p, then it's 3s, slightly higher is 3p, then it's 4s, and then a little bit higher we have the 3d orbital, and so on and so forth, right? So the box notation explicitly writes the electrons where they are in the orbitals, and it explicitly tells you what the spin of the electrons are. So this is basically a shorthand way of saying the quantum numbers, right? So, for example, if we had the element fluorine, fluorine is element number 9 on the periodic table, and so it has 9 electrons. Okay, 9 protons, 9 electrons to balance it out. So we have to place these 9 electrons onto this diagram, right? And so to place it on this diagram, we have to follow 3 rules. Okay, 3 rules. The first rule is what's known as the Aufbau principle. This comes from the German word meaning to build up. Okay, we start at the bottom, the lowest energy, and we build our way up. Okay, we build our way up. So the build-up principle. Second, we have to follow the Pauli exclusion principle. Right? This says that no 2 electrons can have the same 4 quantum numbers. Okay? And finally, Hund's rule. Which states that electrons will separate within the same sublevel. And the reason for that is because electrons repel from each other, they're going to try and distance themselves as much as possible. And the way they do that is by occupying separate orbitals. Okay? So how does this work? Well, we can start placing the 9 electrons. So from the very bottom, that's the Aufbau principle, we'll have 1 electron that's spin up, and so we represent that with a half arrow, and we can't put an electron with another spin up like this. This is not allowed. Right? And this is not allowed because of the Pauli exclusion principle. Notice, we have n is equal to 1, we have L is equal to 0, we have M is equal to 0, and we have S equal to positive 1/2, right? So, both of these electrons share the same set of quantum numbers. Therefore, this is not allowed. So, we can't have the same spin within an orbital. Okay? That's essentially what this rule is stating. So, instead of spin up, we have to have spin down. And now there are no more options for putting electrons into this energy level. All right? So we go to the next energy level, which is 2s. So spin up, spin down. So there's 4 electrons. We have the 2p energy sub-energy level. So this is going to go spin up. Now, according to Hund's rule, we're not going to place it spin down like this, right? Electrons will try to repel. So they'll try to repel from each other as much as possible. So instead of pairing it first, we're going to split it up. Okay? We're going to split it up. So up, up. So there's 6 electrons. We'll do another electron. Again, separate as much as possible. So 7. The 8th electron, it can't really separate from the other 3, so it is forced to pair, meaning it has to be forced to pair down. So the 8th electron, and finally the 9th electron. Okay, so this would be the box diagram, right, for fluorine. All right. So where we're explicitly writing out the spin states of each electron. Okay? So we have the full electron configuration, noble gas configuration, box diagram. There's one more consideration to make, right? And that's for the elements chromium and copper. Those are elements 24 and 29 respectively. It turns out that when we write the electron configurations for this, right, we get 1s2, 2s2. So if you do it normally, you get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And for copper, we get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Okay? Well, it turns out that having the D shell like this, right, where it's almost full. So I'm going to write the 3d orbitals right next to this, where it's almost half full or fully filled. Okay, so if you were to write the box diagrams, this is what the 3D orbital would look like. Well, it turns out that making it half-filled stabilizes it in a slight way. And it stabilizes it enough that it takes one of the s orbital electrons and it plops it into the d orbital. Okay, so the same thing happens for chromium and copper, right? It takes one of those s orbital electrons and it plops it into the d orbital. Okay, so instead of 4s2 3d4, we have 4s1 3d5. Okay, and instead of 4s2 3d9, we have 4s1 3d10. Okay, so in essence, and our final point for this video, S2D4 or S2D9 turn into S1D5 or S2D10 or S1D10. Okay, so that's all of the points about electron configuration. Good luck on the test, everybody. Take care.